Hello, this is Mr. Colati going through lesson 3.5, Newton's third law. I'm going to let you guys go through the PowerPoint and fill in the blanks here, but Newton's third law basically states for every action there is an equal and opposite reaction. You guys probably heard that before. So we have some interesting examples here, but we're going to go down to the actual word problems. A tennis ball hits the wall with a force of 2.4 newtons. Draw a free body diagram for the tennis ball and for the wall. Well, if this is the wall here, oops, and this is my tennis ball, and it's going at the wall, well, let's draw a free body diagram then when they make contact. So I'll do the next picture here. So you can get the contact of the tennis ball with the wall. So at this point, the wall has some sort of force pushing on it, right, from the ball. That's a force applied. This is for the wall. We're gonna ignore for now the normal force and gravity because the wall we don't know much about. Now for the ball, well, at this instant there's some gravity impacting, as always, the ball, but the ball is being pushed by the wall this direction. So there's an applied force this way. Usually what we do is we write FA and then we put a little apostrophe there to show that it's the complement or the pair, the force pair. So this is my action force, this is my reaction force, or vice versa. There are always pairs. For every action force, there's an equal or opposite reaction force. Oh, this was 2.4 newtons to the right. And this was 2.4 newtons to the left. Okay, so let's do a more complicated problem. Mr. Colati pushes a TV on ice with a force of 200 newtons. Assume no friction. Mr. Colati's mass is 75 grams and the TV's mass is 15. Find the acceleration of Mr. Colati and the TV. You have to imagine, if you've ever been on ice, it's very slippery, right? So when we stand on the ice and we push a TV, there's my TV set. The TV is going to go this direction for sure, but when I push off on the TV, I'm actually going to recoil backwards a little bit. Now this wouldn't happen if I had good shoes with good grip, but on a frictionless surface, I actually would go in the opposite direction. So if I draw a free body diagram for Mr. Colati, well, there's FG, why don't we call this C for Mr. Colati, and then this will be FNC for the normal force. So I'll put a free body diagram for Mr. C. And there is an applied force by the TV on Mr. Colati going this way. So we'll call this FA. Probably this is the reaction to his pushing. There's no friction because we've been told this is a frictionless surface. Now for the TV, on the other hand, we have the force of gravity. We'll call it FGT. Note how gravity is a little smaller because the force of gravity is smaller for the TV. It has less mass. Then I'm going to draw the normal force due to the TV. And then there's that pushing force by Mr. Colati, FA. So Mr. Colati pushes the TV, but the TV pushes back with the exact same magnitude of force. So let's look at these two. Oh, sorry. This is 200 newtons, and this is 200 newtons to the right. This is left. It's hard to see. Why don't we define up as positive and to the right as positive? I need my red pen. Okay, we'll have to live with this pink pen for today. This is going to be plus 200 and this is going to be minus 200. Okay. The other givens that we have are, Mr. Colati's mass. So mass of C, or mass of Mr. Colati, is 75 kilograms, and MT is equal to 15 kilograms. And those are scalars. Okay, so let's look at the acceleration of Mr. Colati. So we can make a little heading for Mr. C, or because we've used these little subscripts, we wouldn't need the headings, but it does keep my solution very organized. So we know that this is an unbalanced free body diagram, so we know that the Newton's second law will apply. So we're going to add up all of the forces to find F net in the x direction. And this is equal to the mass of Mr. Colati and the acceleration in the x direction of Mr. Colati. Now if I add up all the forces, I just get negative 200, and the mass is 75, and this is the acceleration in the x direction for Mr. Colati. I'm going to divide, so I get negative 200 divided by 75 is equal to the acceleration. I need my calculator. I have 200 divided by 75. So I get AXC is equal to negative 2.667. Similarly, for the TV, I add up all of the x direction forces for the TV, and that's equal to the mass of TV times the acceleration in the x direction of the TV. I get positive 200, the mass was 15, and the acceleration is what we're solving for. This is 200 divided by 15. If I type that into my calculator, I get 200 divided by 15, which gives me 13.33. So look at what we see here, and we can write our final statement, but the TV really accelerates. And this makes sense, right? If a person that's heavier than the TV pushes the TV, well, the TV's going to go flying. Now the TV pushes back on that person, but because they're a lot heavier, the acceleration of the person is not quite as severe. Therefore, the acceleration of Mr. Colati is 2. Wow, well this is really ugly, 200 newtons, but I'm just going to use, I guess it's one significant digit actually. So this would be 3 times 10 to the 2 meters per second squared to the left. And the acceleration of, oops, what have I done here? 3 meters per second squared to the left, and the acceleration of the TV is 1 times 10 to the 2 meters per second squared to the right. Unfortunate that we had to round to one significant digit, but that is the case because of this number. There you go. Hope that clears up your Newton's third law questions. Make sure you do take a look at the Google Slides to just go over some of these interesting cases about the third law. We'll see you next time. Bye.